Kia ora, Year 11 and 12. In this video, I'm just doing part D2 of question 3 of the Level 2 Algebra exam, which I think was a challenging question for a couple of reasons. And I think it's, as I said in the last video, I think it's a great maths question. I don't really think it belongs in an exam under this much time pressure, but you might disagree. Anyway, here's the question. So in part D1, John Young realised that he could change around the dimensions of the cuboid, and he's taken A units off one side and added A units onto the other side. And the third side has a height of 10. So the height of this cuboid is 10. What we found in part 1, is that if the surface area of the cube is going to be the same as the surface area of the cuboid, right? So the cube is the cube where all the sides... Oh, now I'm going to do bad drawing, but never mind. So all of the sides of the cube have length p, right? And we got this condition for the surface area of the two things to be the same thing. And at this stage, he's playing around with this and looking at what values of A might work. So what we have to do here is to find the largest possible whole number value that A could take in this context. In other words, if he took 1 centimetre off one side and added it to this side, is it going to be possible to have the surface areas be the same? Right. So I'm going to write that one down just to give you an idea of where we're trying to get to. So if the number that he took off and added on was 1, then this would be the condition that we get for the surface areas to be equal, right? And the reason that that's useful is to figure out the dimensions of the cuboid for P. Now all we've got to do is to solve this quadratic, right? So if he adds and takes away 1 unit, then the surface areas will be the same when this holds, and we can find the dimensions by solving that equation. And you could solve that one just from looking at it. I might divide through by 2 and then do completing the square, but most of you guys would probably do the quadratic formula. So what we're interested in here is not what happens when it's 1, but what the biggest possible whole number value of A could be. Now, if we're going to build this thing, the side lengths afterwards have got to be positive, right? So if we're looking at it, we know that that one's 10, and we know that when we've got the A added to it, we're going to be bigger than P. But if A is too big, if A is bigger than P, then we're going to have a negative number here. And we don't want that to happen. But the way they've suggested that we approach this question is by using the discriminant. So let's start from doing it that way. And I'm going to show you how actually that's not going to be quite enough to get the right answer. So looking at the quadratic equation, we've got 2p squared minus 20p plus a squared is equal to 0. Let's chuck that into the quadratic formula and see what we're getting for p. So p is going to equal this, and the a, b, and c are my coefficients in here. Right, so a is 2, b is negative 20, and c is a squared. Now the question suggests that we use the discriminant, and that's definitely going to be important, right? So p has got to be greater than 0, and it has to be a real number, right? Because we're going to be actually using it to build a cube or a cuboid. So that means that the discriminant has got to be positive, right? Remember all of that lovely level 2 work about when the discriminant is negative, we have no real solutions, is what we're going to be using here. So the first thing to do here is to say, well, let's see what happens if we put on this condition that b squared minus 4ac is greater than or equal to 0. Right, so that seems like the way to go, because that is going to tell us when we're going to have real solutions for p. We only need one of them, so it would be okay to have b squared minus 4ac equaling 0. I'm going to do that, and then I'm going to show you why that's not enough. Okay, so b squared minus 4ac here gives us this. Negative 20 squared minus 4 times 2 times a squared is greater than or equal to 0. So it's 400. No, that's not right. Is that right? 4 times 2, not 4 times 8. So 400 minus 8a squared is greater than or equal to 0, giving me 400 is greater than or equal to 8a squared. So 50 is greater than or equal to a squared. So rewriting that for our brains, a squared has to be less than or equal to 50, but he's taking something off. So we're going to say, you know, a is greater than 0, just because in this context, look what he's doing. He's adding something on and he's taking it off. Now, a could be a negative number, and then, you know, this side would be the long one and this would be the short one, but that's not going to get us far. So we're just going to say a is a positive number. Hopefully there's no maths teachers watching this for that very garbled explanation. But what that means is that we can say a squared has to be between 0 and 50. And so the biggest possible value of a is going to be 7, right? Because 7 squared is equal to 49. So that's great. And that's what they've suggested that you do. And we've used the discriminant, and it looks like we've found the largest possible whole number value that a could take on. So that's all good, but there's a problem. And the problem will become apparent when we do this. So use this value of a to find the dimensions of both the cube and the cuboid and explain your reasoning carefully. So when I did this question, I used the hint about using the discriminant. And if that hint hadn't been there, I don't think I would have done it that way, right? So I'm going to show you now what goes wrong when a is equal to 7. And if you've got a graphics calculator, you can figure that out pretty quickly. So we've used the discriminant and we've got a is equal to 7. But now we have to find the dimensions of the cube and the cuboid. I just need a bit of working space for this. Okay, so we're solving now. 2p squared minus 20p plus 49 equals 0, right? And we're doing that because a is equal to 7. And so from here, we're going to get the value of p for the cube. And then we're going to get p minus a and p plus a. So solving that, we get the following things. You know what? I'm going to pause this and I'm just going to chuck that into my calculator, which is not near me. I have to run and grab it to show you that one of the problem we're going to get here is p is going to be fine. P will be positive, but when we take 7 off it, it's going to be a negative number, which doesn't make any sense. Okay, sorry about that. I'm back and I've got the numbers that we need. Right, so chucking this into the quadratic formula, what do we get? Well, p is equal to negative b, so 20 plus or minus the square root of b squared, so 400 minus 4ac, right? And we know from the discriminant work above that it's 400 minus 8 times 49. And I think it's fine, actually, if you'd solved this in your graphics calculator at this point as well. Who knows? I haven't seen the schedule yet, but I did it kind of by hand way because that's what I always do. So we've got p is equal to 5 plus or minus the square root of 8 over 4. Right, so we can choose either of those numbers, right? So we're going to pick the big one for p because we're going to be more likely to be able to take a off it. But even if we pick the big number for p, so we get 5 plus or minus 0.7071. So using p equals 5.7071 and a is equal to 7, we hit trouble, right? Because p minus a is 5.7071 minus 7. Now, I tell you, if I'd been sitting in that exam and I'd got to that point and figured it out, I would have freaked. I would have thought, oh, I've done something wrong. What's the problem? Well, the problem is this, right? So you can see that you can't go much further because you can't build the cuboid because this works out to be negative. Oh, no, I can't do that in my head. It's about negative 1.3 or negative 29 something, blah, blah. Okay, but we've got trouble. So let's go back and think about why just finding the discriminant was never really the right thing to do here. The discriminant's important, right? Because if you don't have a positive discriminant, you don't get any solutions. But we should have imposed, quite simply just said, well, p minus a has got to be bigger than 0. So if you solve the problem that way, then you are actually going to get to the right answer. The other alternative is that what could you do when you've tried 7 and it didn't work? Well, you weren't that far off, right? P minus a was a negative number, but it wasn't that negative. So probably most of you will have just have gone, if anyone had time to do this. Let's try a equals 6. Now, it turns out that a equals 6 is the correct answer, but if you're doing maths and you're doing this kind of maths, that's pretty unsatisfying. So let's look at how we can show that a equals 6 is indeed the right answer. Don't know if anyone's still watching, but here's what we really need to have. We need to have p minus a is greater than 0. We know that that's going to be the longest side that we need. So p has to be greater than a. We know what p is. We've already worked that out from before, right? So we've got this quadratic 2p squared minus 20p plus a squared equaling 0. That's the condition for my surface areas to be equal. So p is 20 plus or minus the square root of 400 minus 8a squared over 4, and that's got to be greater than a. Now I'm going to work with the big number for p here because it's going to make it easier to be okay, right? So I'm going to now say we can justifiably not worry about the low value of p. So choose bigger p to work with, because we just need to get one p value that's going to make the surface areas equal. So we've got 20 plus the square root of this, and that's got to be greater than 4a because I'm multiplying everything through by that. Square root of 400 minus 8a squared is greater than 4a minus 20. I'm going to square both sides. 400 minus 8a squared is greater than 4a minus 20 squared. 400 minus 8a squared is greater than 16a squared minus 160a plus 400. Now, for lots of you watching, especially if you're watching this from maybe level 3 or you did it last year, you'll notice that you can take out a common factor here of 4, right, and square that first. So there's some factorizing and stuff we can do here differently, but this is kind of the clunky slow way just to do that expansion. Right, now looking at this, it's starting to look a bit better. If we subtract all of this side, we're going to get 0 is greater than 24a squared minus 160a. And look, the 400s have gone. So we're just about there. And we've got 0 is greater than, let's see, divide both of those by 4, 6a squared minus 40a, divide them again by 2. We've got 3a squared minus 20a. This is looking really nice now, right? So that's what I mean. This is a really cool question. It's just quite a lot to get done in the time with the rest of the paper. So a times 3a minus 20 has got to be negative. So think about your parabola. You've got a quadratic inequality. You've got one root at 0, and you've got this one here. So 3a minus 20 equals 0 gives us a is equal to 20 over 3, which is 6 2/3, right? So a has to be let's see. Yeah, if a is less than 20 over 3 between those values, then our condition is satisfied. So the maximum value of a is 6. And now we still have to find the dimensions of that thing, right? So we've got p is equal to 5 plus or minus the square root of 400 minus 8 times 36, right? And you could be divided by 4. You could be chucking that into your graphics calculator if you wanted to at this point. So you've got 2p squared plus, what was my equation? Sorry, 2p squared minus 20p plus 36 equals 0 is what we're trying to solve. And if you do that, the values you get for p is, this comes out to be p is equal to 7.65, I guess it's centimetres or metres. And so p minus a is equal to p minus 6, which is 1.65 centimetres. I'm about to run out of time. And p plus a is equal to 13.65 centimetres. So the cuboid dimensions are this, and 10. And the cube dimensions are this thing here. All right, thanks for watching. I hope that made some sense. Please let me know if it did or didn't. And that's it for the algebra exam.